And now we'll turn to the final submodule within this unit, and that is a brief discussion of how Verilog operates internally. While it's not essential to know this in order to be a designer, I consider it to be useful background information, and in addition, the language does make reference to items such as triggers, and this will help explain some of the nomenclature. So let's look at a piece of code here. Here we have 3 statement blocks. Always at pos edge clock, A equals C and D. Always at A, G is the OR of producing a 1-bit result from the input of A. And assign F equals E hat E, which is an exclusive OR gate. I haven't fully specified what this is. You don't know what the bit widths are and so on. But it doesn't matter for the purposes of this exercise. The question is here, how does this simulate? More specifically, this will be simulating on a serial computer, which can only do one thing at a time. On the other hand, we want to capture the parallelism of hardware on this computer and capture the behavior of the parallel hardware properly on a serial computer. So how do we do this? First of all, we need to understand how changes in variables trigger the other statement blocks here and the sequence in which that occurs. So initially we have a rising edge of the clock. That obviously triggers the always at pos edge clock statement, which then in turn changes A. When that changes A, it triggers these other 2 statements that must look as if they change in parallel. And the question is, how do we create the appearance that F and G change at the same time? Well, this is a brief overview of how that happens. So here we have those 2 statement blocks that we want to have appear as if they're changing at the same exact moment in the simulator time, that is, the time you see on the screen in the simulator. The way that is done is as follows. When A changes, the simulator essentially freezes time, freezes the simulator time, while it goes off and works out all these parallel bits of hardware and how they're going to behave. In order to work that out, without seeing the variables change on the screen, it basically uses hidden internal variables to sequentially evaluate what they will be, and they might even change during that evaluation, but you'll end up with a final answer once you've evaluated all the underlying code that supports the always at and assign at the top. You'll end up with a final answer at the end of this period. Once that is done, once you've evaluated all the code that must appear to change at the same time, then the actual variables are assigned all at once, and you'll see, and then the simulation time is unfrozen, and you'll see G and F changing simultaneously in the simulator. Now this is a simple example. Later we'll see more complex examples where there's a long chain of events within, for example, an always at block that will appear as if they're being evaluated in one moment of simulation time. So the RTL really only specifies clock level timing when you think about it. All logic in the RTL is 0 delay. Now, what I see is this often confuses students. They first of all, they see that and they're going, wait a minute, we just had this big long section in timing. Where's all the timing? Well, you can't get combinational logic delay until you know what the gates are. At this point, we don't know what the logic gates are. The other common problem I see is it worked in pre-synthesis simulation. Now with actual delays, it doesn't work. And of course, that can happen because in pre-synthesis simulation, you could actually specify that for I equals 1 to 1024, do 1024 multiplications, and you can set up the simulator quite happily so you can do that in 1 femtosecond. Just specify 1 femtosecond clock. And of course that's impossible. No logic could be that fast. So it really, despite whatever you write as the clock period, is immaterial in a sense in pre-synthesis simulation. You could set the clock period as being 1 century. As long as you don't also do that in the synthesis run, it's actually okay. At least I think. There might be some problems with that longer time. So pre-synthesis, there's no such real concept of delay. Really what you're looking at is a clock level simulation, much like we did in the revision notes. Pre-synthesis, because of this, the signals will all look like they're changing right on the clock edge. Look at this example here. We have a rising clock edge here, and the outputs, which are these bottom two here, are changing right on that rising clock edge. Again, this is because of the zero delay in combinational logic. Now initially you might be a little confused. You might be wondering, is this really changing right after the clock edge or right before the clock edge? And the answer is you should think of them as changing right after the clock edge, i.e. those bottom two waveforms here are either the Q outputs of flip-flops, which are changing instantaneously after the clock edge, or logic that derives from them. So that brings us to the end of this quite short submodule. I'll remind you the basics of how Verilog operates. We have these triggers that trigger the statements and statement blocks. The triggers come from what's listed in the always at content, or for always at start is worked out, and the right hand side of the size, the variables on the right hand side of the sides. Verilog keeps track of these triggers and know what they trigger, and is constantly looking to see if any of these triggers are exercised, i.e. they change elsewhere in the code, or in the case of the pos edge clock, change with a positive edge. When that happens, the Verilog simulator assembles all the code fragments that were triggered at that particular instant. It freezes time, it uses internal hidden variables to evaluate how those code fragments behave. Once everything has finished evaluation, it then assigns those internal variables back to the visible variables and turns back on the simulator clock so you can see the results on the screen. What I suggest you do now is go to the quiz for this particular subunit or correction for this particular submodule before going on to the next major unit in this Verilog 1 module. Thank you very much.